Hello there, I am Victor, ESR14 for the PersonalizeAF network.
Hi, I'm Cristian, ESR7 from the same network.
We are here at Maastricht University, my host institution during my PhD, for Christian secondment.
I come from the KIT in Germany. I'm going to be working with you guys for 3 months.
Yes, we both work with computer models, but we do have very different approaches to it.
So my work here is to collaborate with you guys to create a bridge between both models and take the advantages of both.
Here in Maastricht, we work mostly with what we call reaction diffusion computer models. In these models, we simulate mathematically the behavior of many currents that go in and out of the cardiac cells, associated with the different ions that are responsible for the electrical conduction in the heart. If we do that for several cells, we can have a realistic simulation of these currents propagating from one cell to the next. We can arrange the cells in different shapes to do experiments of various complexities. In my work here in Maastricht, we use a volumetric model of the human heart that shows many details of the anatomy and can conduct these electrical signals in 3 dimensions. Working with these models demands a lot of computer power to solve all these equations that represent the conduction for a high number of cells. In order to do that, these simulations have to be run in supercomputer, which have a very high capacity to deal with a huge amount of data in a short time frame, making these experiments possible.
Now I will explain the Iconal model, that is the model that I have been extending during my PhD. It's very similar to the reaction diffusion in some aspects. It requires similar input. Instead of the conductivity, we use the conduction velocity directly from every node in the geometry. We need the fiber direction of the muscles in the heart, and we need the geometry of every patient's heart. That could be from MRI or from electroanatomical mapping. And then we put all this information into some equations, an elliptical differential equation that solves for activation times here for t, and takes as an input the conduction velocity, that is here the f, and uses the d, that is the anisotropic tensor, that tells us that the propagation of the heart is faster in the fiber direction here by lowercase f, and is slower in the transversal direction by some radio k. Then the output is only the activation times, in line different from the reaction diffusion, where we have the transmembrane voltage for every node and every step on time. Here we only have the activation times for every node, and that's why it's less detailed, the model. But the Iconal model is still a potential alternative, and the reason for this is that it performs faster simulations. Not only the equations are a bit more simple, but it also allows for using coarse mesh. So instead of representing the heart with 2 million, 4 million nodes, we could represent it with a small amount of nodes, let's say 100,000. And here we can see how we have bigger triangles to represent the same heart, the same shape, instead of having the smaller triangles. And because it is fast, there could be potentially used in the future in the clinics to guide ablation procedures in cardiologists. Then the reason why it is still not used is because it neglects several mechanisms that I have been trying to overcome during my PhD. And one of the most important things that normal or standard Iconal models being used to do is to reactivate nodes. So every time that a node was activated in the simulation, that was it. So this is how I have been working in reactivating these nodes. And that's one of the important limitations that I have overcome here. And now it's time to use more complicated simulations like biatrial or whole heart simulations. Now let's talk about the project that we will do here more in detail. The first thing that I will want to do with my new model is to validate my results. For that, we will use Victor's results here that are more sophisticated with a model that has been validated before.
Yes, the model we have here gives a more detailed output, so we have a lot of information about the conduction patterns in the heart. So we'll start off by conducting a very simple experiments like reproducing the conduction patterns we would see in a healthy patient.
Then, when I have these results from Victor in this healthy patient and very simple simulation, I will try to replicate the same results using my model, with the only exception that the mesh would be more coarse with less nodes. All the other conditions will be as similar as possible. And then taking both results from both models, we would hope that the activation times will be as similar as possible.
Yes, and once this is working and adjustments have been done, then we can start introducing some more complexity that will make our simulations more similar to what we actually see in atrial fibrillation. So we can start introducing fibrosis in our anatomy and some electrophysiological remodeling, so that we can start to have more complicated patterns like rotational patterns or transmural breakthroughs.
Once I have these more complicated experiments from Victor with patterns of fibrosis, rotors, and breakthroughs, I will try to validate my model again in this new configuration of experiments. And then when the validation stage is finished, we could move forward to the next step, where the idea is to perform a high number of experiments with different patterns of fibrosis to analyze new aspects of atrial fibrillation.
Yes, and if you want to keep updated about these results that we will obtain here during our collaboration here in Maastricht, be sure to follow PersonalizeAF social media, where we post the latest results of our research. And until then, see you next time.
Bye.